Hey, everybody. Okay. So to start with the first lecture here, where do we begin in astronomy? Well, I think it's a good place to start with some basic ideas, some basic definitions and concepts of what do we talk about when we talk about astronomy? What are some of the ideas that we use, and we're going to be using these over and over again all semester long, um, so that we can understand context and the scale that we're operating on. Um, to to give you a sense here, um, here's a bit of a Russian nesting doll view of the universe, where we say, okay, so here's the Earth. All right, home sweet home. We're familiar with this. And if you zoom out from the Earth, then it turns out the Earth is just one planet of several planets orbiting around the sun. And that constitutes the solar system, right? The solar system is the sun and all the smaller things orbiting around the sun, planets, comets, asteroids, and then all the moons that are orbiting around those planets. The sun is a star, and then if we zoom out some more, the sun, it turns out, is just one of hundreds of billions of stars in our whole galaxy. So our galaxy we call the Milky Way galaxy for historical reasons. Um, the galaxy is made of, as I said, hundreds of billions of stars, and it is of which the sun is just one. And in our galaxy, there are probably billions. Actually, the recent estimates say that there's something like a trillion planets in our whole galaxy. Why am I saying all this? Right? This is basic definitions, but more important than that, if you don't know that much about the types of objects in astronomy, then people use the term solar system and galaxy interchangeably because they don't know the difference. But the solar system and the galaxy are two very different things, right? Our solar system has one star, the sun. The galaxy has hundreds of billions of stars. Our solar system is big compared to the Earth, right? Compared to the Earth, our solar system is huge, but our solar system is tiny compared to the entire galaxy. So when we talk about solar systems versus galaxies, we are operating on very different scales of size. We're operating in very different contexts. So that's why I'm starting the class talking about this, is to say it's not just a bit of vocabulary, because that's boring, that's something you could look up, but why do we use this vocabulary? Astronomy is weird. One of the things that you're going to pick up on over the course of the semester is that astronomy is it's a little weird. And it operates a little differently than other science classes you're taking because we are operating on huge scales. And all of these huge scales, I mean, they're huge, but they're different than each other, right? A planet versus a solar system versus a galaxy versus a cluster of galaxies. If we zoom out some more, it turns out that our galaxy is just one of a few dozen galaxies within the local group of galaxies. That's what it's called. It's called the local group, and it's a cluster of several galaxies. A few dozen galaxies. Each of those galaxies has billions of stars. And it turns out that our local group is actually a pretty small cluster because our local group is part of the local supercluster of galaxies, which is made of thousands of galaxies, each of which has hundreds of billions of stars, a trillion planets, other lots of small stuff. And then the local supercluster is just one supercluster in the entire visible universe, which is much bigger and much farther away even than the local supercluster. So from the very smallest stuff like our entire planet, which in this diagram is pretty small comparatively. Zooming out, all the way until you look at the very distant galaxies at the edge of the universe. We're zooming in and zooming out. We're operating on very different scales. We're looking at things in very different contexts. And so it's important to start off just getting our feet wet and saying, well, how do we talk about this? How do we talk about this in a way that helps our understanding? All right, so that's where we're going to start today. Okay, here's something a little bit more familiar. This is the southern sky as seen from Arizona, obviously, in winter. So if you go out tonight, you're probably not going to see these constellations because it's summertime right now as I'm recording this. If you look for something familiar, you might recognize that this is the constellation Orion. And if you get a little bit of practice reading star charts, I don't expect you to know this right off the top of your head, but if you get a little bit of practice, you'd know, okay, if I can identify this as Orion, then to the left of Orion, this constellation is Canis Major, and this constellation over here, sort of going out of frame, is Taurus. And so these a little bit of familiarity with star charts can help you find some things you might want to see, such as, let's see, if you can identify Orion, then this bright reddish-orange star up here is called Betelgeuse. This one down here is called Rigel. Off over here to the left, the brightest star in Canis Major is called Sirius. Sirius is the brightest star in the night sky. And off to the right here is this star over here is called Aldebaran. Aldebaran, the red eye of Taurus, the bull. So it's the red bright star in the whole constellation Taurus. So we're going to get a little bit more practice with this in the next couple of days. But, once you can identify something familiar, a constellation, and then you could say, well, okay, what else do I know that's in this area of the sky? And then you can get a little bit of practice knowing the names of stars and other things like that. Not everything in this picture is a star, though, right? There's lots of stars in this picture, but actually, if you look at Orion's belt, and if you look at a little bit south, that pinkish orange object right there is not actually a star. That is, if we zoom in, that's the Orion Nebula. So the Orion Nebula, this is our first little bit of vocabulary here. What is a nebula? Well, what does this look like? What does this object look like? It looks like a cloud of gas. So that's what a nebula is, right? A nebula is a cloud of gas floating out there in the galaxy. It's nothing more complicated than that. There are different kinds of galaxies, so not every galaxy looks the same. In fact, every galaxy looks a little bit different, which is one of the things that makes them interesting. But specifically this, the Orion Nebula, this is the kind of nebula where stars are born. So all of these stars that you're seeing, well, all of these stars in the foreground, all of these bright stars that you're seeing over here, these are all new stars, brand new stars that were just born out of the gas of this nebula. Now, when I say these stars are newborn, how old do you think they are? How old do you think a brand new newborn star is? Well, they're a few million years old. So that's young by star standards, right? A few million years is young by star standards. So this is a different context, right? If we say here on Earth, talking about people, if we say, oh, it's a newborn, well, that's not millions of years old, is it? But stars can live for millions or billions of years. And so to say, oh, that star's only a few million years old, oh, it's still young. That's a context, right? That's a scale that we need to get used to operating on these really long cosmic timescales. And in fact, out of this nebula, several hundred stars have been born already. And actually, if we look inside the nebula, which we'll do in a few days, there are stars that are still in the process of being born. right now, today, in that nebula. So there are, in this nebula, a few hundred newborn stars. And yet, if you're looking at this with the naked eye, those several hundred newborn stars all just look like one little pinkish blotch on the larger night sky. So when you look up at night, it's not just stars that you see. I mean, you could see the planets, obviously, or the moon, or the sun if it's daytime, but also galaxies and nebula and lots of other objects. So it's good to get a little bit of a sense of vocabulary so that when I say solar system versus galaxy versus nebula versus planet, right, these are very different objects because they are very different sizes, very different distances away from us. They're made of very different stuff by and large. And so getting a little bit of practice with what these words mean and what they're like, it's not just vocabulary for vocabulary's sake. It's knowing what we're talking about so that when we talk about these things, they mean something. All right. So that's we're going to start that today, and we're going to be working on this for the whole rest of the semester. This picture here is what's called the Hubble Extreme Deep Field. This is one of the deepest images ever taken. Using the Hubble Space Telescope, they pointed the Hubble and stared at one spot in the sky for days and days. Just letting that light soak up. Pointing that telescope, using the Hubble Space Telescope, they pointed this telescope at one spot in the sky and just let whatever light wandered into the not wandered, it's light, it travels in pretty straight lines, but letting whatever light entered the telescope get absorbed by the camera for days. And when they downloaded the image from the telescope, this is what you find. This tiny square, and I mean, it doesn't look tiny because it's taking up your whole computer screen, but this one image, if you were looking at this spot with the naked eye, this one square is about the size of a quarter if I were holding that quarter 150 feet away from you. So imagine that somebody is holding a quarter in their hand, but they're standing 150 feet away from you. It would look pretty tiny, right? That quarter would look pretty tiny on your vision. And yet, whenever you look deep into the blackest, emptiest parts of the sky using telescopes and letting that telescope absorb light for these long lengths of time, what do you see? Thousands of galaxies. Every light source in this image is a separate galaxy, except two. Actually, there are two stars in the foreground in this image. Can you find them? There are two nearby stars in the foreground of this image. Right there and right there. You can always tell a star in a Hubble image because they get those spikes. Like this, those what are called diffraction spikes. Now, obviously, a star does not have big spikes coming off of it, right? If you look at the sun, don't look at the sun with the naked eye. But they don't have stars. The spikes they're an artifact of the camera. They're basically an artifact based on the shape of the telescope and the shape of the camera. It's sort of like a lens flare. It's just light bending as it enters the telescope, and so it creates those trails, those spikes where the light bleeds across the camera. So you always know in a Hubble image, you always know if you're looking at a single star because they get spikes like that. Everything else in this picture, everything that doesn't have those diffraction spikes, is something much bigger, much farther into the background. So everything, all these big things, but also all these tiny things. Every speck, every smear, every smudge, every swirl, everything in this picture, besides those two stars, is a separate galaxy made of billions and billions of stars, much, much, much farther away. And this is just one little square. There's a little over 5,000 galaxies in this one little picture, the size of a quarter held 150 feet away. So that when you try to think about, well, then how, if there's this many galaxies in this one little picture, how many galaxies are there in the universe? And if each galaxy is made of hundreds of billions of stars, how many stars are there in the universe? And pretty soon these numbers just become incomprehensibly large. This is one of the problems of astronomy. And I don't mean problem as in like I don't mean problem as in like a detriment. I mean learning astronomy for the first time, or learning it for the 20th time, like some of us experts. One of the persistent obstacles to really getting good at astronomy is that the numbers just become incomprehensibly big. At some point, the numbers of galaxies, the numbers of stars, the distances to these things, these numbers just become so big that you can't wrap your head around them. So how do you do it? Right? How do you get from being overwhelmed by these giant numbers? Well, we've got a few tricks. Right? Just because you can't exactly wrap your mind around the question of like how many stars there are in the whole universe doesn't mean we can't get a handle on it. Right? We have some tricks to cheat, essentially. We're going to cheat and say, let's not do that. Let's not do the thing that our brains just can't handle. Let's cut through the business, cut through the problem, and get right to the answer in a way that means something to us. What's that? What are some of these tricks that we have to help us wrap our heads around these numbers? One of those is scientific notation. If you remember way back whenever you were taught scientific notation the first time, right? Remember that scientific notation is all about what power of 10 the number you're dealing with is. Where you say, oh, okay, well, 10 to the 0th power is 1, 10 to the first power is 10, 10 to the second is 100, 10 to the third power is 1,000, 10 to the fourth power is 10,000. Scientific notation is a code, right? Scientific notation is a code that takes really big numbers and squishes them down so that you can deal with these big numbers in ways that don't just become a giant mess of zeros and commas, right? If you give me a number like 89,000 and you write down 89, 000, you're like, all right, this isn't like too big, but this number is starting to get on the edge of what's a little too big for me to intuitively deal with. Like, can I intuitively picture 89,000 of something? If I gave you a pile of 89,000 marbles, how big would it be? I don't know. Like, I can wrap my head around like a pile of 10 marbles. I can maybe wrap my head around like a pile of 100 marbles. But if I said I'm going to give you my collection of 89,000 marbles, how big of a table would you need to hold that? Because I don't know. Right? So, at some point you start writing down commas and zeros, and it becomes more trouble than it's worth. So what do? How do we deal with big numbers without losing our sense of perspective, without losing our sense of scale? That's what scientific notation is all about. Because you say, okay, I'm going to turn this into 8.9 times 10 to the 4, where 10 to the 4 is 10,000, and 8.9 times 10,000 is 89,000. But what have I done? By converting into scientific notation, what have I done? I have separated the important information from the details. Because here's the thing. When you start dealing with astronomy, and you start dealing with huge numbers of objects that are really big and really far away and really hot, and the numbers just become big, 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 I don't care that much about the details. I mean, I care, but I care about that last, right? The first job, your first job when you're trying to figure something out is just wrap your head around it. Try to surround the problem and figure out what you're dealing with, right? Try to get a sense of approximately how big this thing is, approximately how many. Okay? That's the first job, right? The first job, whenever you're dealing with these really big numbers, is what does it mean? What does this number tell me, approximately? Give me a ballpark idea of what that number means, and once I've got an idea of the general case, then I can deal with the details. Then I can worry about exactly how many whatevers I'm counting, right? If you told me, or if I saw a picture of how big a pile of 10,000 marbles was, if it was like, oh, okay, well, I need my dining table to hold 10,000 marbles, then that would mean I needed 8.9 tables to hold 89,000 marbles. Okay, I can wrap my head around that. Right? The whole point of scientific notation is that it is a code that separates the important information from the details. The important information is that little number right there, right? The power of 10. That's the most important piece of information, because the power of 10 tells you approximately how big this number is. Approximately how big is this number? Oh, it's a few tens of thousands, right? 8.9 is a few. If you gave me 8.9 apples, that's a few apples. So this number is a few tens of thousands. How many tens of thousands? Details. Right? If I'm doing some calculation and I need to worry about the details, I'll worry about the details later, after I've figured out what's going on. Right? That number there out front, the 8.9, it's a few, right? That's the details. Worry about that later. Look at the power of 10. It tells you how big this number is. It tells you the scale you're operating on. It tells you the context that you're operating in. Okay? Scientific notation is also great for doing small numbers, right? 10 to the negative 1 is 1/10. 10 to the negative 2 is 1/100th. 10 to the negative 3 is 1/1000th, right? So if you give me a number like 0.0066, how big is that? I don't know. It looks small, right? 0.0066. I don't have an intuitive feel for like how big that number is. It's small. I agree it's small, but how small? I don't know. Small? But if I turn this into scientific notation and I say 6.6 times 10 to the negative 3, okay, 6.6 is a few. 10 to the negative 3 is 1,000th. So how big is this number? Oh, it's a few thousandths of something. However, whatever that number is talking about, it's a few thousandths of something. Okay. I'm starting to wrap my head around this. I'm starting to get a sense of what I'm talking about. Okay, that helps. Two quick asides that will become helpful as you're working on the homework. One is when you're doing math with scientific notation, either for the homework or for the final project, you're going to be dealing with scientific notation. because it makes life easier. But a machine like your calculator or your computer does not handle scientific notation the same way we do, the same way we're taught math. Computers use scientific notation with this using the letter E. E for exponent, right? E for the exponent on 10. Right? So I call it machine code, but or E notation. Honestly, I don't know what the actual term for this is. This is what happens when you only take 2 computer science courses in all of college. But basically, you've probably seen this before come out of your calculator or your Excel spreadsheet or something. But what am I looking at here? Right? If I wanted to put in 8.9 times 10 to the 4th, right? You could, in your calculator, you could type out 8.9 times 10 caret 4, and your calculator would do it right if you typed it out correctly. Right? We've all made those mistakes of typing things out in the wrong order, and the math comes out wrong. Your calculator will, and you probably should, use that E instead. Right? So you could just put into your calculator 8.9 E4, and your calculator would read that as 8.9 times 10 to the 4th power. Okay, the E stands for times 10 to the power of whatever comes right after it. Right? So if you wanted to put in 6.6 times 10 to the negative 3, you just put in 6.6 E negative 3. All right? You can do this in your calculator. You can do this in an Excel spreadsheet. You can even do this into the number bars, into your answer bars in Smart Sparrow. So if you're putting in some big number in Smart Sparrow, and you will be, or some very small number, you could, if you had to write out a million, right? A million is 1 followed by 6 zeros, right? So you could, if the answer to a question in Smart Sparrow was a million, you could type into that answer box, you could type in 1000000, and as long as you put in the right number of zeros, you'll get the right answer. If you put in the right number of zeros. Or you could just put into Smart Sparrow 1E6. Boom, done. Right? Because 1E6 means 1 times 10 to the 6th power. Okay? Now, I don't know what kind of calculator you have, but there we go. Okay. Here's my little calculator program on the computer, but it probably looks something like this, right? Now, there are probably multiple buttons on your calculator that use the letter E. One of them might be this lowercase e. This is not the one you want, all right? E is a transcendental number. It's an irrational number, right? Much like pi, right? The lowercase e is the letter that stands for 2.71828 da la 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 la. It's a constant. All right. This is not the number you want. Most calculators have this double E for exponential notation, like it says right there. All right. That's the number you want in your calculator. So if you put in your calculator 1E or EE3, what does that mean? It means 1 times 10 to the 3rd power. What is 1 times 10 to the 3rd power? It's 1,000. Right? That's how you can do scientific notation in your calculator. Rather than typing into your calculator all those zeros and comma. I mean, you usually don't put in commas, but do this, get some practice. It'll make your life easy. All right? Slide number 2. Significant digits. Why do we use significant digits? Why does the homework ask you questions about significant digits? If you were like me growing up, which you probably weren't because I was a weird kid, arguably still am, but whenever your teacher, junior high, high school, whenever it was, whenever they were teaching significant digits, they're like, oh, you've got to round to this number of significant digits. And you probably said, but why? And sometimes the teacher would say, oh, no, round to 2 or 3 or 4, and I don't know if you went to the same school that I did. They're like, oh, no, just round to 3 significant digits. Why? I don't know. Right? Here's the thing. Significant digits are very important. As I became a professional scientist, it turns out they're very, very important because significant digits are about honesty, right? The number of significant digits that you round to is not arbitrary. Your math teacher or chemistry teacher or whoever it was in school was just picking a number that seemed to make sense. In real science, you don't just pick an arbitrary number. You can't be arbitrary about it because significant digits are all about honesty. Significant digits are about you reporting the accuracy of your answer. Because if you're doing a calculation, your answer cannot be more accurate than the least accurate of your inputs. Right? Your answer to a problem can't be more accurate than your sloppiest measurement. So if your measurements are sloppy, your answer comes out sloppy. If your measurements are very precise, with many significant digits of accuracy, then your answer can be more accurate. So, for example, right, let me just give you an example here. Let's say you're doing some calculation. You make 2 measurements. One measurement is 17, the other measurement is 215.1. And then to do the calculation, you divide these 2 numbers. And if you take those 2 numbers, 17 divided by 215.1, you plug that into your calculator, and your calculator spews out 0.0790330008. If you write that down as your answer, you are a liar. Okay? Why? Because if you write this down, you're saying, what is this? What is it? 3, 4, 7, 9 decimal places, right? If you write this down as your answer, you're saying you did this experiment, you did this calculation so well that you are able to answer this question to 9 decimal places of accuracy. And you are a liar. Because your answer is based on these 2 measurements. How many significant digits are in this measurement? 2, 1, 7. How many significant digits are in this measurement? 4. All right. Which of those 2 numbers, which of those 2 measurements is more accurate? The 215.1 is, because it's got 4 significant digits of accuracy. So this number has 2 significant digits. This number has 4 significant digits. Your answer cannot be more accurate than your less accurate measurement. So you need to round your answer. You need to take this answer from your calculator, and you need to round it to the less accurate measurement, to the less accurate degree of significance. So you're going to round your answer to how many significant digits? 2, right? 2 is the less accurate measurement, or the 17 is the less accurate measurement because it only has 2 significant digits. So you need to round your answer to 2 significant digits. And then when you look at a number like this, you're like, wait, so is 2 significant digits, is that 0.1, or is it 0.08, or is it 0.079, or where do I cut this number off so that it's 2 significant digits? The other thing I remember when I was being taught significant digits the first time is that there's all these rules for zeros, and sometimes a 0 is significant and sometimes it's not significant, and I don't remember which one because it's not something you need to do. There's a cheat. There's an easier way to simplify this. You're not going to write this down, but the easy way to figure out where to round is turn it into scientific notation. Take this number, convert it into scientific notation, and it would become 7.90333088 times 10 to the negative 2. And then you say, okay, now I'm going to round this to 2 significant digits. 1, 2, boom, I'm done. There's your answer. 7.9 times 10 to the negative 2, that's the right answer. To the right, rounded to the right degree of significance. Right? You got the right answer, and you're reporting it accurately. You're reporting it honestly to say, this is my answer as accurate as I am able to justify given the precision of my measurements. All right? So when you're writing down an answer, when you're doing some math, like you're going to do for the homework, or like you're going to do in some of the tutorials, like you're going to do today, do not give me calculator vomit, right? Don't write out all of these digits that your calculator spews out because your calculator doesn't know where it needs to round. That you need to figure that out, right? Your calculator is dumb. You need to be smarter than your calculator. Don't write down all those digits. Round to the right number of significant digits. And the right number of significant digits is whatever your less accurate measurement is. Okay? Okay. Aside's over. There's another cheat. Cheat's not the right word. There's another trick that we use to simplify these issues in astronomy. When the numbers get too big, make up a more convenient unit system. Make up a more convenient system of measurements to measure astronomy. For example, when you measure distances out, well, if you wanted to measure the distance to the sun, right? The sun is, well, you know, it's a lot farther away than Tucson, right? So one measurement, so you could measure the distance to the sun in miles, you could measure the distance to the sun in kilometers, and the numbers get really big really fast. They become unwieldy large. So we're going to invent a unit to measure astronomy. We're going to call it the astronomical unit. Very creative, I know. One astronomical unit is defined as the distance from the Earth to the sun. So what is an astronomical unit? An astronomical unit is the average distance from the sun to the Earth. One astronomical unit is equivalent to 93 million miles, or 150 million kilometers, or 1.5 times 10 to the 8 kilometers, because these numbers are getting pretty big already, right? We're just talking about the distance to the sun. The sun's, in the grand scheme of things, the sun isn't even that far away, and yet we're already operating on the scale of tens of millions of miles, hundreds of millions of kilometers. We got a bunch of zeros and commas here, and that's just the distance to the sun. So scientific notation helps simplify that considerably. Or you could measure the distance to the sun as one astronomical unit, right? If you're measuring, if you want to know, okay, how far away is the sun? Do you want to measure it in 93 million miles or 150 million kilometers, or one AU, one astronomical unit? Yeah, one is a number I can wrap my head around, right? One is a number that gives me a more intuitive feel. All right, so when we talk about distances to objects in our solar system, if you're measuring the distance to the sun, Mars, Jupiter, things in our solar system, we're not going to use miles, we're not going to use kilometers, because those distances just get too big too fast. We're going to measure the distance to the sun and the planets in astronomical units, because the numbers stay reasonably small. Once you get outside the solar system, once you start talking about the distances to other stars, astronomical units get too small. And we need to shift gears again. When you start measuring the distances to other stars out there in the rest of the galaxy, we measure those distances in a unit called a light year. Okay, what is a light year? A light year is the distance that light travels in a year, right? Because light travels at a constant speed, light travels at the speed of light. And since light travels at the speed of light, then the light is going to travel a fixed distance in a fixed amount of time. That is, light travels 1 light year of distance in a year of time. How big is a light year? Well, a light year is about 9.46 times 10 to the 12 kilometers. Right. That's 9.5 trillion kilometers. That's how, light travels really fast, right? Light is the fastest thing in the universe. And so light travels 9.5 trillion kilometers in 1 year. That's about 63,000 astronomical units, which is why we don't measure the distances to stars in astronomical units. Because here's the thing. 1 light year doesn't even get you to the next star over. The nearest star to our solar system is called Alpha Centauri, or Proxima Centauri actually is the closest star in that system. Proxima Centauri is a little over 4 light years away. So 1 light year, 9.5 trillion kilometers, doesn't even get you to the next star. It takes 4 light years. So if you're measuring, and that's the closest star to us, to our solar system. So when you start talking about scales and numbers getting ridiculously big, do you want to measure the distances to the nearest stars in trillions of kilometers, or hundreds of thousands of astronomical units, or 4 light years? Yeah, 4 is a number I can wrap my head around, right? This is why we have these different units. Fundamentally, the rule of thumb is you want to have the right tool for the right job, right? Use the right tool for the right job. Use whatever tool makes life easier. If you're measuring distances around our solar system, use astronomical units. The numbers stay reasonably small. But if you're talking about distances to other stars, we're going to shift gears and we're going to measure those distances in light years, or for reasons that we're going to get into in a couple of days, we also measure distances to stars in parsecs, where a parsec is a little more than 3 light years. So sometimes we measure the distances to stars in light years, sometimes we measure it in parsecs. Why would we do one over the other? Because sometimes light years is easier, sometimes parsecs is easier, and you want to have the right tool for the right job. How will you know what the right tool is? We'll get there in a couple of days. They're all measurements of length, right? Kilometers, miles, astronomical units, light years, parsecs. These are all just units of length, units of distance. But sometimes we're going to use one or the other, whichever one helps us understand what we're talking about, whichever one helps us understand the context that we're dealing with. Pick the scale, pick the system of measurement that helps us wrap our heads around what's going on and where are things without us getting bogged down in these giant numbers. All right? To reiterate what I've been saying here for a minute, right? Kilometers are fine, right? Miles or kilometer, miles are fine, but this is a science class. We're going to be mostly using the metric system. So, kilometers are fine. If you're talking about distances around a planet or a moon, but once you start talking about around the solar system, right? 1 AU is the distance from the sun to Earth, which means once you start talking about distances out to Jupiter, Saturn, Uranus, right? Once you start measuring the distances out to the other planets, here's the distance from the sun to these other planets, right? Earth is 1 AU from the sun, Mars is 1.5, Jupiter's 5. All the way out to like Neptune is 30, right? Neptune is the farthest planet from the sun, and yet, you could say, oh yeah, the distance to Neptune is blah, blah, blah billion kilometers. Or you could say 30 AU. 30 is a number I can deal with. It's still billions of kilometers, but if you're just trying to figure out where things are, if you're trying to get a mental image of where these things are in the universe, in space, in relation to each other, pick a convenient unit system. Okay, Earth is 1 AU from the sun, Mars is 1.5. Okay, I can picture that. I can draw a cartoon. I can wrap my head around that. Right? I can handle these numbers because I've picked a system, a unit system, that keeps the numbers manageable. Once you start talking about stars and galaxies, then we need to shift gears again. This is a cartoon, obviously. This is an illustration. This cube here is the space in the neighborhood of our solar system. So here's the sun. And then here are all these nearby stars. How far away are these nearby stars? Well, they're a few light years away. How many light years? Details. A few, right? The exact distance in light years is not the important thing. The scale, right? How big are we talking? How far away are these stars in relation to us and in relation to each other? Oh, these stars are a few light years away from us. Okay. I can imagine that. I can draw an illustration. I can get a sense of where things are. Because these are nearby stars. Nearby stars are a few light years away. Once you zoom out and look at the entire Milky Way galaxy, the whole Milky Way galaxy is about 100,000 light years in diameter. So we're not living in the big bright downtown of the galaxy. We're living sort of out here in the nice quiet suburbs. Our solar system is about 28,000 light years from the center of the galaxy. So, what did I say a second ago? Nearby stars are a few light years away. Far away stars that are in very far away neighborhoods in some other part of the galaxy, those are thousands of light years away. Tens of thousands of light years away. We also use this trick to measure things like size, because we're going to be operating. Once you start talking about planets and stars, we deal with very different scales of size, right? Okay, here's the Earth, right? The Earth is the biggest of the small planets, right? Earth is big compared to Venus, Mars, Mercury. But Earth is small compared to Jupiter. And, if you wanted to measure the size of Earth in kilometers, okay, that's not so bad, right? The Earth is, what is it, about 6,000 kilometers, 4,000 miles in radius. Okay, 4,000, 6,000, that's not too big. But if you start saying, well, Jupiter is blah, 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 hundreds of thousands of, let's see, what would it be? Okay, tens of thousands of kilometers. If I told you Jupiter is 100,000 kilometers in radius, how would you know if I'm right? How would you know if I'm telling you the truth? Right? If I just tell you, oh yeah, Jupiter has a radius of 100,000 kilometers, and you would hear 100,000 kilometers, and first off, you'd say, well, how big is a kilometer? I don't know, I'm American. But even if you had a familiarity with how long a kilometer is, you would say, oh yeah, 100,000 kilometers. Okay, I guess that sounds big. I know Jupiter is big. I guess that's right. How would you fact check me? If you don't know how big 100,000 kilometers is, how do you know if I'm too big? How do you know if that's too big? How do you know if that's too small? How do you know if I'm right? We need a unit system that doesn't have you lose perspective. Because if I just start throwing around 100,000 kilometers here, 100,000 kilometers there, how, I'm probably going to start losing perspective. That sounds big, but is it too big? Or is it not big enough? I don't know. I've got no sense of scale. But if I tell you, okay, I'm going to invent a new unit, just like we did it before. I'm going to invent a new unit for measuring the size of a planet. I'm going to call it 1 Earth radius, where 1 Earth radius is the radius of the Earth. And so, what's the size of the Earth? I'm not going to measure it in miles or kilometers. I'm going to say, how big is the Earth? 1. 1 Earth radius. That's the radius of the Earth. Okay, well, how big is Jupiter? Jupiter is 11 Earth radii. Okay, 11 is a number I can wrap my head around. And if I show you a cartoon that says, here's Earth, here's Jupiter, and you say, oh yeah, Jupiter has a radius 11 times the radius of Earth. Okay, that sounds right. Right? You can fact check me. You can see if that makes sense or not. If does that look too big? Does that look too small? Does that look just right? Without getting bogged down in all the zeros and commas. So measuring the size of a planet in Earth radii works well, right? Works well for planets. It works well in that context. But once you start zooming out, right, Jupiter is a lot bigger than the Earth, but Jupiter is tiny compared to the Sun. Right, here's the size of the Sun. I'm not going to measure the size of the Sun in Earth radii because now the numbers are starting to get pretty big again. So I'm going to shift gears and I'm going to invent a new unit system. If I wanted to measure the size of a star, like the Sun, I'm going to invent a new unit. I'm going to call it 1 solar radius, where 1 solar radius is the radius of the Sun. All right, so how big is the Sun? Oh, the Sun is 1 solar radius. Okay, that's, 1 is a number I can handle. Here is the size of Sirius. Now, I know it's been a few minutes, but remember, Sirius is the brightest star in the night sky, right? Sirius is that bright star in Canis Major, just to the left of Orion. How big is Sirius? If I just started throwing out numbers, oh yeah, it's this many miles, it's this many kilometers, you'd go, yeah, that doesn't mean anything. Oh yeah, Sirius is blah, blah, blah million kilometers in radius. And you'd shrug and go, I guess so. I don't know. But if I told you how big is the radius of Sirius compared to the radius of the Sun? If I'm just eyeballing it, if I'm estimating, because that's more important than details, I would say 2 times, right? What's the radius of Sirius? Oh, it's 2 solar radii, right? It's 2 times however big the Sun is, which is, a detail you can look up if you need to. Whatever the radius of the Sun is, Sirius looks like it's twice that big. Okay, that sounds about right. And you'd be right. Right? Sirius is big compared to the Sun, but Sirius is small compared to Aldebaran, the red eye of Taurus the Bull, that reddish-orange star that's just to the right of Orion. Right? Aldebaran is what you call a red giant, because it's pretty red, and it's giant compared to the Sun. Right? How big is Aldebaran? If I just started throwing out millions and millions of kilometers, you'd be like, yes, big, no. Is that too big, too small? I don't know. But if I say Aldebaran is, oh gosh, what is it, 44? Right? Aldebaran is like 44 solar radii. Like, oh, it's 44 times the size of the Sun. Oh, that's why it's called a giant. Right? Aldebaran is huge compared to the Sun, but Aldebaran is tiny compared to Betelgeuse. Betelgeuse, that bright reddish-orange star at the top of Orion. Betelgeuse is what you call a red supergiant, because it's red and it's supergiant, right? Betelgeuse is something like 300 solar radii. It's 300 times the size of the Sun, right? 300, now we're getting into big numbers, but not too big, right? A number that we can still wrap our heads around. So this is what we're going to do when we measure the size of stars. You're not going to measure it in kilometers or meters or miles or feet, because why would you do that? Why would you do that to yourself? Let's just measure the size of stars compared to a star that we know, like the Sun. That way, not only do the numbers stay more convenient, but those numbers mean something. If I tell you Aldebaran has a radius of 44 solar radii, okay, 44 is a number that's not too big, but also what does that mean? It means Aldebaran is 44 times the size of the sun. And you look at that and go, oh, well, that's why it's called a giant. It's not just about the numbers being convenient, it's about preserving meaning. When we zoom out to galaxies, like we're going to do toward the end of the semester, this is the Andromeda Galaxy. This is the next big galaxy over. Right? This is not our galaxy. This is the next galaxy over. This is the closest galaxy to our Milky Way galaxy. Andromeda itself is made of hundreds of billions of stars. And how far away is Andromeda? Andromeda is about 2 million light years away. Let me just say that again so that it sinks in, right? Andromeda is the nearest galaxy to ours, and it's 2 million light years away. So when I say, and I've been doing this the whole time here now, right? When I say things like near versus far, big versus small, young versus old, the first question that should come into your head is, compared to what? Relative to what? In what context? Right? What's the context that we're dealing with here? Because a nearby star, how far away is a nearby star? A few light years away. How far away is a nearby galaxy? A nearby galaxy is a few million light years away. Very different scales because they're very different contexts. All right? So, again, if this isn't all sinking in right now because we're going pretty fast here, we're going to get some practice over the next month. Because once we get toward the end of the semester and we start talking about galaxies and galaxy clusters and the whole universe, we're going to have plenty of familiarity with these units of measurement, so that when we start throwing these things around, hopefully, we'll know what we're talking about. Right? In order to understand the universe, we need to have plenty of tools in our tool belt. Right? We need to have a bunch of tools in our tool belt that help us figure things out without getting lost in the details. And having these convenient units of measurement and scientific notation and having these tricks, these are basically tools to help solve the big problems of the universe in a way that makes sense, in a way that means something, in a way that we can wrap our heads around so that we can say, that's what this is. Stars, galaxies, nebula, planets. What are these things? How do we know? Where do they come from? Where are we going? What is our place in the grand scheme of the universe? This is the journey that we're all starting on today. All right. Kilometers, AU, light years, millions of light years, billions of light years. These are units of distance. But they're also, let me say one more thing, because this is relevant to the homework for you. These distances are also timescales. These are also measurements of time. Because remember, what is a light year, right? A light year is how far a light travels in 1 year of time. So that, to go back here, the Andromeda Galaxy is 2 million light years away. Well, how far does light travel in 1 year? In 1 year, light travels 1 light year. That's the definition of a light year, right? So how much time does it take for light to travel 2 million light years? 2 million years. If you go out tonight and look at Andromeda, which you'd have to live pretty far into the desert for it to get dark enough to see it. You can see Andromeda with the naked eye if you live somewhere really dark. But if you go out and look at Andromeda tonight, you're not looking at Andromeda the way it actually is tonight. Right? You're looking at Andromeda the way it was 2 million years ago. That light to go to the little cartoon here, right? That light left the galaxy 2 million years ago. It's been traveling for 2 million years, and it just got there tonight. Just got here tonight. When you start looking at galaxies really, really far away, right? What did I say? Nearby galaxies are only a few million light years away. But these galaxies in the Hubble Extreme Deep Field, these galaxies are billions of light years away, right? These little red smudges here and there. What's the farthest galaxy in this picture? I think it is. I think it's that first one that I looked at. I think it's that one right there, if memory serves. These faraway galaxies, the galaxies in the extreme background, these galaxies are billions, with a B, billions of light years away. And that means that those galaxies, that light took billions of years to get here. That light left that faraway smudge of a galaxy, that little smudge in the very background of the image. That light left the galaxy billions of years ago. It's been traveling through space for billions and billions and billions of years, and it's just reaching us here on Earth now. The farther away you're looking, the further back in time you're looking. So if we're just talking about stars and planets, this isn't that big of a deal, because stars are only, if you're looking at individual stars, those stars are only thousands of light years away. And, stars don't change that much in thousands of years. So we can be fairly confident, not completely confident because we don't know yet, but we can be fairly confident that if you're looking at a star tonight, that's pretty much the way it looks right now. We don't know what it's looking right now. We can only see a star the way it did look when that light left the star. But since that was only a few thousand years ago, the star is probably the same as it is right now. But these galaxies, these faraway galaxies, that information is arriving at us billions of years late. What are these galaxies like right now? What are these faraway galaxies? What are they like right now? We don't know. We're seeing the way they were billions of years ago. What we're looking at, when you look at these, they don't look like much, right? You really pay attention to like, the big pretty galaxies, right? This there and these ones over here. Okay. But if you look at those tiny ones, the little smudges in the background of the image, what you're looking at are the baby pictures of the universe. Right? Those galaxies, the farthest galaxies in this picture, it's probably not that big red one. It's probably these even smaller ones like that one there. That's what all galaxies used to look like billions of years ago. The farthest galaxies in this picture are about 13.2 billion light years away. Meaning we're looking at those galaxies the way they were 13.2 billion years ago, when the universe was 13 billion years younger. We don't know what those galaxies look like today. We can't know what those galaxies look like today. They're too far away. That light hasn't reached us yet, but we can see what they were like in the past. When you're trying to figure out where did the universe come from, how did the Big Bang happen? How has the universe evolved and grown and changed from the Big Bang to today? We don't have to guess, right? We don't have to just speculate. We can know what the universe was like 7 billion, 12 billion, 14 billion years ago. We can look at them. We can look into the past, right? A telescope is not just a big fancy camera. A telescope is a time machine. It lets you look into the past to see what the universe was like back then. All you got to do is be able to look far enough away. So that's the other scale that we're going to be operating on all semester long. Not just scales of distance and size, but time. Right? Because again, if we start throwing around a million years here, a billion years there, it's all just going to sound like big numbers, but they're very different contexts. So getting a little practice with that helps us get our feet wet. It helps us get a little bit of practice with these issues so that as we talk about them all semester long, it'll make some sense. Okay.